Imagine this. A spacecraft, sleek and sophisticated, embarks on a journey to Mars. It's a marvel of engineering, designed to unravel the red planet's secrets. But then, disaster strikes. The spacecraft breaks apart, shattering into a million pieces. What went wrong? The answer lies in a fundamental principle of physics, Newton's third law. This law, often paraphrased as "for every action, there is an equal and opposite reaction," governs the way objects interact. It's a simple concept with profound implications. In the case of our ill-fated spacecraft, a miscalculation of the forces involved led to its destruction. The spacecraft's thrusters, designed to propel it through the vacuum of space, exerted a force. But according to Newton's third law, an equal and opposite force was exerted back on the spacecraft. This reactive force, if not properly accounted for, could be catastrophic. And in this case, it was. This dramatic example highlights the importance of understanding Newton's third law. It's not just an abstract concept confined to textbooks. It's a fundamental principle that governs the motion of everything in the universe, from the smallest particles to the largest celestial bodies. Let's break down Newton's third law a bit further. It states that for every action, there is an equal and opposite reaction. But what does this really mean? It means that forces always come in pairs. When you push on a wall, the wall pushes back on you with an equal force. When you jump up, you're actually pushing down on the earth, and the earth is pushing back up on you, propelling you into the air. Every interaction involves an exchange of forces, equal in magnitude but opposite in direction. Now here's where the confusion often arises. People often misinterpret the law to mean that these equal and opposite forces cancel each other out. But that's not quite right. The forces act on different objects. Think back to the example of jumping. The force you exert on the Earth has a negligible effect on our planet because of its massive size, but the Earth's equal and opposite force on you is what launches you into the air. The forces don't cancel, they create motion. The Tacoma Narrows Bridge collapse in 1940 is a stark reminder of what happens when we fail to respect the power of Newton's third law. The bridge, once a symbol of engineering prowess, was reduced to a heap of twisted metal in just a few hours. What caused this catastrophic failure? It wasn't just the wind, as many initially believed. It was the wind's interaction with the bridge's structure, an interaction governed by, you guessed it, Newton's third law. The wind, flowing over and under the bridge, created forces that caused the bridge to oscillate. These oscillations, in turn, created additional aerodynamic forces. This cycle continued, with the oscillations growing larger and larger until the bridge could no longer withstand the stress. The Tacoma Narrows Bridge serves as a cautionary tale. It reminds us that even the most impressive feats of engineering can crumble when we fail to account for the fundamental laws of physics. It underscores the importance of understanding and respecting the interplay of action and reaction. Section 4. Reaching for the Stars. Falling Short of the Laws. Early Rocket Science Blunders. The early days of rocket science were marked by both exhilarating breakthroughs and spectacular failures. One of the biggest challenges was understanding how to control the massive forces involved in launching a rocket into space. Early rocket pioneers quickly learned that Newton's third law was not to be trifled with. The force required to lift a rocket off the ground generated an equally powerful force pushing back down on the launch pad. If not properly accounted for, this force could have disastrous consequences. There were explosions, crashes, and near misses. Rockets veered off course, spun wildly, and sometimes even exploded on the launch pad. These failures, while frustrating, provided valuable lessons. They highlighted the importance of careful design, precise calculations, and a deep understanding of the forces at play. Section 5. From drones to deep space, modern marvels built on Newtonian foundations. Today, our understanding of Newton's third law has allowed us to achieve incredible feats of engineering. From the sleek drones that navigate our skies to the powerful rockets that propel spacecraft to distant planets, Countless technologies rely on the principles of action and reaction. Take drones, for example. These unmanned aerial vehicles stay aloft thanks to the force generated by their rotating blades. As the blades push down on the air pushes back up on the blades, creating lift. The faster the blades spin, the greater the force, and the higher the drone can fly. Or consider spacecraft propulsion systems, which use the expulsion of high-speed gases to generate thrust. As the gases are expelled out of the back of the spacecraft, they exert an equal and opposite force, propelling the spacecraft forward. This is how we explore the cosmos, venturing farther and farther into the vast expanse of space. These are just a few examples of how modern technology relies on a sound understanding of Newton's third law. By harnessing the principles of action and reaction, we've been able to achieve things that were once considered the stuff of science fiction.